Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting concept of attention sinks and then talk about how you can do language modeling with attention sinks so as to model input sequence lengths of 4 million plus tokens. These days, large language models brag about being able to handle very long sequences. How do they handle them, right? So what is this concept of attention sinks? So let's talk about what are attention sinks, why do they even occur, and why are they problematic in that senses. Okay, so what you see here in the top picture is basically attention heat maps of autoregressive models, specifically Llama 2 7 billion parameter model. Okay, with inputs of sequence length 16. So the inputs of length 16 were passed, and you basically obtain like attention heat maps of different layers and different heads. So this is for layer 0 head 0, layer 1 head 0, layer 2 head 0, and then you see different layers all the way up to layer 31 head 0. Okay. So what do you observe here? You observe that except for the first two layers, layer 0 and layer 1, where there is not much of an attention which is being paid to the first few tokens. You look at layer 2. The first token is all red. Red basically means very high attention. Okay. Look at layer 9, layer 16, layer 23, layer 31. The first token is basically absolutely red. Okay. Uh, and the remaining few tokens, the first few tokens also basically they have high attention values, not red, but still high attention values. So the observation is that um, except for the first two layers, layer 0 and layer 1, where the first token does not really have extremely high attention values, and the token and the pattern is more local. You see, the pattern is more local in that sense. Is local tokens actually have more attention values. In higher, as you go higher and higher layer, you observe that the local tokens do not seem to have high attention values. In fact, a very high attention is being given to the first token. Okay, very high attention is being given to the first token across various heads. I mean, here it is basically just being shown for head 0. Okay, so strong attention scores basically are being observed towards initial tokens, and that is why these initial tokens can be referred to as attention sinks. Okay. Now, why would this be happening? Well, this happens because in some cases, basically for a particular word which is self-sufficient by itself, you do not want to pay any attention to other tokens in that senses. But softmax unfortunately allocates this unneeded attention somewhere, and it constrains things to sum up to one. And that is why basically, since the first few tokens are the most observed in the autoregressive modeling, all of this attention mass sort of seems to basically take up or seems to be allocated to the first token or the first few tokens. Okay. um, Now let's talk about what implications does it have on various kinds of attention. So as we all know, there is dense attention, which basically means every token in autoregressive modeling basically pays attention to every other token in the past. Now this one basically has poor efficiency because if your input sequence length is, let's say, 1024, you would need to do 1024 squared computations, which is huge in that sense, right? And therefore the performance on very long text, where the text is greater than the pre-training size of the pre-training sequence length of the original model, it basically just drops significantly. Okay. Then there is window attention, and window attention is very popular for being very efficient, right? So you basically just keep L cached tokens, and then you compute window attention based on these. You compute attention based on only the previous L tokens. Okay. But there is also this sliding window attention with the recomputation. Now, what this means is that you don't really use the cached versions of these previous few tokens, the key value caches, but you actually recompute these key value caches based on only the current sliding window. So whatever is the window, you basically compute the attention only based on, you compute the attention only based on the sliding window itself. So notice that the sliding window and the window attention, they're not exactly the same. They're different because in the window attention, you could basically have computed these key value pairs and the attention on these key value pairs based on the context, the previous context, which is no longer available in sliding window. In sliding window, the only tokens that are available are the tokens in the current sliding window, right? and therefore the recomputation needs to be done. And interestingly, apparently, it looks like if the window size is long enough, then sliding window with recomputation actually leads to better accuracy or lower perplexity, significantly lower perplexity compared to window attention. Yeah. Window attention, the perplexity sort of drops significantly as soon as the first token or the first few tokens are evicted from the cache, right? So as you basically get to the eighth token, for example, the first few tokens get evicted, and the window attention's perplexity really increases significantly compared to recomputation, where the perplexity drops significantly. Yeah. Now, streaming LLM is basically an attention sync based method. So having realized that the first few tokens are super important, why don't we basically compute attention with respect to not just the local window, but also on the first few tokens, right? And when you do that, the streaming LLM basically has lower latency. Essentially, it's not squared in terms of the input sequence length, but basically it's multiplication of it's of the order of multiplication of the input sequence length multiplied by the window size, right? And it has very good accuracy or lower perplexity. Lower perplexity is better, obviously. Okay, so that's that. Now, in the lower plot, what you see is these perplexity values drawn with respect to different input sequence lengths up to 20K. And as or lower the perplexity, the better it is. And you have values, basically the series or rather the plots shown for dense attention, window attention, and streaming LLM. Okay. So what you observe is that streaming LLM is such a simple idea. Essentially, pay attention not just to the local context, but also to the first few tokens in the input sequence length. Okay. And as you can observe, streaming LLM basically has the perplexity values staying flat, staying lower, even when you go up to sequences of 20K. However, if you notice the dense attention, well, the dense attention guy basically suddenly has a very high perplexity as soon as your input sequence length goes beyond the pre-training length. It also has, a window attention also gains very high perplexity, which is bad, right? As soon as basically, the input sequence length is greater than the KV cache size, in which case the first few initial tokens are evicted from the cache. Okay. So this is a plot for Llama 2 7 billion. The paper also has plots for other models. However, they're not really as vivid as this plot. Since Llama 2 uses rope embeddings, this particular effect is even more stronger. Okay. So how does the streaming LLM solve the attention sync problem? Well, as I mentioned in the previous slide, streaming LLM basically just says that, hey, to solve the attention sync problem, keep the key value caches of the 4 attention sync tokens. So the first few tokens are called attention sync tokens. Just keep those caches also, plus the sliding window caches. So for example, to generate the token 9, you're going to pay attention not just to 6, 7, 8, but also to the first 4, 0, 1, 2, 3, and so on. So 0, 1, 2, 3, you basically pay attention to them always in that senses. Okay. So interestingly, streaming LLM basically has almost similar perplexities as sliding window with recomputation, but sliding window with recomputation is 22 times slower compared to streaming LLM, and therefore streaming LLM makes a lot of sense. Okay. While doing this, usage of attention sinks and the rolling KV cache, you have to ensure that you basically recompute or rather re-index the positions in that senses. So for example, in this particular case, you're not going to call the positions as 0, 1, 2, 3, 6, 7, 8, but you're going to basically really call these positions as 0, 1, 2, 3, 4, 5, 6 in that senses, right? So essentially you give the position IDs again based on whatever positions you are using. So in some ways you make the model feel that these attention sinks are not really far away, but actually just prepending to the current rolling KV cache. Okay. So, you can observe that if you do the streaming LLM thing, which does not really require any pre-training change or any fine-tuning change, only, at runtime, at inference time, you're basically just prepending the attention sync tokens also. You observe that across different models, Llama 2, Pythia, Falcon, and MPT, the perplexity stays low, even for sequence lengths of the size of the order of 4 million tokens. Okay, so even for 4 million tokens across different model sizes and across different model families, you observe that the perplexity remains pretty low in that sense. So streaming LLM retains the accuracy and lower perplexity of these models. Okay, so so what you see here is basically what happens if you vary rather than using just the first attention sync token. How about why do you use 4 tokens? Why not just use like 1 token, 2 tokens, 3 tokens, and so on? Okay, so this is what you see in this table below. For different models. using 0 tokens, 1 token, basically how many sync tokens do you use, right? So as you can observe, if you just use 0 sync tokens, that's basically like window attention, and you observe that the perplexity values are pretty high. With one sync token, you basically observe, that the perplexity sort of reduces significantly, but it's not really, saturated. So if you use two, it basically decreases further in some cases. And then if you use four, basically, at least for llama to 7 billion, you sort of observe that with four attention sync tokens, the perplexity has sort of saturated in that senses. And that is why they propose that you must use like 4 attention sync tokens, and that's good enough. Okay. Now, interestingly, these window sizes of the window attention do not matter too much. In fact, they observe that with Llama itself, if you basically rather than using a 4,000 sized window size, if you basically bring it down to 2,000, that actually gives you lower perplexity. And the perplexity is not really very high, even if you bring it down to just 1,000 tokens. So yes, sliding window attention size, people have tried to experiment with different size of attention windows, but yes, I mean the attention sync kind of the formulation seems to work even when your window sizes are smaller rather than very long, very long. Okay. Now, using 4 tokens is great, but hey, can we pre-train models also and rather just use the first attention token in that senses? So therefore, they also experimented with a very interesting thing where they say that, hey, at pre-train time, how about I pre-train with just by designating the first token as an attention sync token? Okay. So, and this concept is actually very, very similar to the register tokens that people have started using while pre-training the vision transformer models in that senses. Okay. So in this particular case, they pre-train with just one attention sync token, the first token, and they pre-train Pythia 160 million parameter models. They designate the first token as a global trainable designated attention sync token. So essentially, it's a trainable embedding. So you randomly initialize and train it by a backpropagation. Okay. Um, and when you do this, what you observe is that if you pre-train without the sync token versus you pre-train with sync token. So without the sync token, as you can observe, the local attention is lower. I mean, in the lower layers. So this is layer 0, layer 2, lower layers. The local attention is observed. A huge lot of local attention is observed in lower layers. But as you go to higher layers, you observe a very highly increased attention to the initial tokens in deeper layers, in layer 10 and so on. Okay. But with sync token, what do you observe? You basically observe that attention is directed to the sync token starting from layer 0 itself. So you basically see attention to the sync token is pretty high and across all layers, and less attention is basically being provided to the other initial tokens. So the other initial tokens get less attention, which is what you expected it to have in that senses. Okay. Now, the idea is that if you use this sync token, essentially, you no longer need to have like first 4 tokens in the cache. You could basically do sparse attention or window-based attention with just one sync token. If you do not use a sync token, obviously you have very high perplexity. But if you use a sync token, the perplexity values start dropping just from the first token itself. You don't really need more tokens to have dropped perplexity values, right? So if you basically were pre-training without, if you are pre-training with the vanilla attention, obviously your perplexity values, if you use streaming LLM, this is streaming LLM, vanilla streaming LLM, right? You observe that the perplexity values are lower, but are reasonable. But then, when you use learnable sync, essentially with just one sync token, your perplexity values can be pretty low in that senses. Okay. And learnability and learning with this attention sync kind of a technique does not really lead to any reduction on downstream tasks. So basically, if you evaluate the accuracy of these models on various tasks, these are various natural language processing tasks, you observe that with the sync token, none of these tasks suffer. So that's not a problem at all in that senses. Okay. So that's basically that. Now, how does streaming LLM perform on streaming QA and streaming eval benchmarks? So basically, so what is streaming QA? Streaming QA basically, there are these two benchmarks, streaming QA and streaming eval, which are basically long sequence benchmarks in that sense. So what is streaming QA? Streaming QA basically means you take these two data sets, arc challenge or arc easy, right? These two data sets. And for each data set, what you do is to concatenate all question answer pairs. So basically, it may have like several question answer pairs. You concatenate these hundreds of question answer pairs into a single sequence. And then basically give it to the model and predict the answers at answer positions. And at each answer position, you evaluate how good the model is performing using exact match accuracy. Okay. Now, since the sequence is very long, dense attention basically means that these models, Llama to 7 billion, Llama to 13 billion, Llama to 70 billion chat, all of them basically give out of memory exceptions. Okay. Window attention basically gives you poor accuracies, as you can see here, but streaming LLM basically gives you very good accuracies, as you can see here. Okay. So in fact, these accuracies that you see here are equivalent to one-shot accuracies when you basically provided these examples one by one to these models. If you gave the examples one by one, well, the sequence length is small, and therefore these models perform really well across ARC challenge and ARC easy benchmarks, right? And these accuracies are retained even when you concatenate everything and give it as a single sequence if you do streaming LLM kind of evaluation. Okay. The other evaluation that they do is on this stream eval benchmark. So stream eval benchmark basically is this benchmark where you create a sample of this kind. This is one of those samples in the stream eval benchmark where basically you say below is a record of lines I want you to remember. You give like 20 lines. And then after the 20th line, and you give some numbers, some values for it to remember across these 20 lines. Okay. After the 20th line, basically you ask, hey, what was the content in line 0? So you ask it for the content 20 lines back in time. Okay. And then you basically give 10 more lines and you ask the model to tell the content in the 10th line, which is again 20 lines back in time. Yeah, after 30th line, 10th line is 20 lines back in time. Similarly, after 40 lines, you ask the content in the 20th line, which is 20 lines back in time, and so on. Okay, the model is supposed to remember what was the number which was mentioned 20 lines back in time. Okay, and this is a desired output. Okay. So on this benchmark, as you can observe, these are the results using different models like Llama 2 model, Llama 2 chat 7 billion and 13 billion. There is also these long models which have been trained on very long sequence lengths, pre-training sequence lengths. Okay, so what do you observe? You observe that across these different models, the streaming LLM basically retains very high accuracy scores. You see, very high accuracy scores. Okay. However, the dense attention and window attention suddenly drop in terms of accuracy scores. Dense attention sort of drops as soon as your pre-training length, as soon as your input length goes beyond the pre-training length. And the window attention sort of starts dropping in terms of accuracy as soon as your input length goes beyond the KV cache size when the first few tokens are evicted from the KV cache. Okay, so that's that. So in short, in this video, we talked about attention sinks and the inefficiency or worst performance of window attention in that sense. Window attention for long sequences, right? So window attention worsens when the initial tokens get excluded when your sequence length basically increases beyond the KV cache length. Okay. Window attention with recomputation can retain that accuracy. However, recomputation is expensive. It takes a lot of time, especially when the window size is large, right? Streaming LLM essentially adds attention sinks with recent tokens, and that's a super simple idea, essentially. But the effect is really awesome. It decouples the LLM's pre-training window size and its actual text generation length. It sort of performs really awesome, even with 4 million tokens in that census. Pre-training with a dedicated sync token sort of improves performance, right? Although, I mean, I would think that in this paper, pre-training idea is sort of sold a little more. I mean, I don't know if really anybody would bother, retaining four attention sync tokens versus one attention sync token. Probably 4 is also equally okay. So I'm not sure if pre-training is really, really required. But in general, the idea of using the first few attention sync tokens along with the most recent window based attention, most recent or most local window based attention is a great idea, which basically helps them model very long sequences. Okay, that's it. That's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.